Мгм.
А это хорошо.
Мгм. Хорошо.
Спасибо. Если что-то не так, то скажите нам, мы тогда...
Хорошо. Мгм. Спасибо.
Но там удар будет много. Ничего, это новое.
Понятно. Понятно. Сначала I thought at first that this would be better, but it turns out it's worse. I thought she was coming to tell me it's new and improved, but no, she was coming to say it's broken. Okay, so yeah, I'll try to do it over there. And closer to the other side. That's counterintuitive. Huh? No what? What? And then zoom. Okay. That's probably as good as it's going to get. Let's that piece. Okay, so today we'll finish the last change of rings theorem and talk some more about basic commutative algebra. Then next week, the faculty is closed. And then the following week, we'll start on finer things about homological algebra over a local ring. So actually, one of the goals today is to define what's called a regular local ring. And we'll give the commutative algebra definition. And one of the goals eventually is to give a homological characterization. It explains one of the reasons regular local rings are important. Okay. So let me start with third change of rings theorem. So if you remember what these change of rings theorems were about, it was saying you had some ring, some element in there, which was typically a central non-zero divisor. You have some module, and you want to know how the projective dimension of the module changes, either under restriction or induction. And in general, you just get some kind of inequalities or inequality plus some number. But for a regular Noetherian local ring, we can do better. So it says the following. So a commutative Noetherian local ring. We won't ever talk about Noetherian local rings outside the commutative case. AM, it's a finitely generated module. and X in the maximal ideal of the local ring, this should be a non-zero divisor in both A and on M. So meaning multiplication with this element is an injection. So those are the hypotheses. And then the assertion is that projective dimension modulo X so I think it was called second change of rings theorem. This says this is no bigger than what it was over A. But under this additional hypothesis of local, I get that this is actually exactly projective dimension over A. Okay. So proof. So by the second change of rings theorem, we have this inequality. The new projective dimension of the induced module is no bigger than it was. And there are two proofs of this. You could say that. You could also say it's just the image of multiplication by X. So either way. You mean here? Yeah, I would say the ideal. Okay, so there are two proofs of this. One is the kind of proof we've been dealing with where you write down some short exact sequence for the induction, you see some Tor term vanishes, and then yeah. Mm-hmm. Mm-hmm. I'm afraid if I zoom, I'll have to keep changing it every time I move boards, and that's not going to happen. Okay. I want to give a little bit of a different proof, which is special to local rings. It uses this notion we had of minimal resolution. So let's suppose yes. So I guess I could worry about the infinite case. It doesn't matter. Okay, so suppose M F0, F1, and so on is the minimal projective resolution. If M has finite projective dimension, then this terminates. Otherwise, it might go on forever. So let this be the minimal, be a minimal resolution. Remember, any two of them were isomorphic. And now I claim that if I tensor this with A mod X, I again get a minimal resolution. This on F dot gives a minimal resolution of M mod XM. So there are two things we have to check. We have to check that it's still a resolution and also that it's minimal. So the fact that it's minimal is easy. Remember, minimal just meant that the differential vanishes modulo the maximal ideal. By definition, that's what minimal meant. So to check that it's minimal, you use that x is in M, and so you can reduce modulo M in two steps. First reduce modulo x, and then reduce modulo the rest of M. So reduce mod x, then modulo the rest of M, and it vanishes. To check that it's still a resolution, this is where we use something. So we'll do this kind of term by term. So consider the 0th term, and it has some kernel, K1. And consider K1 is surjected onto, so these are all short exact sequences. K2, and so on. Okay, so now tensor these with A mod x. And in the first one, I'll get the thing I want, M mod x, and then F naught mod x. So that's the beginning of what I think should be the projective resolution. Then K1 mod x, and then a Tor term. So we got I'm just going to write K1 mod x and F naught mod x. I should really write x times K1 and so on. So I get this, but what is this? This is 0. Because what is it by definition? This is F sorry, what is this? This is F in A. Sorry, this is M in big M, such that x, little x times M equals 0. That follows from, take the standard resolution of A mod x and tensor with M. Then there'll be this Tor1 term out there, which will be the kernel of the map M to M, which is multiplication by x. So that's how we use this hypothesis over and over again in the previous proofs. And this is 0 by definition, that x is an unzero divisor on M. Okay? And next, similarly, we'll have K1 mod x surjected onto by F1 mod x, then K2 mod x, and then also a Tor1 term. A mod x and K1. And this is again 0. Because K1 is a submodule of F1, F1 is free, therefore K1 has no 0 divisors on it. So this is since K1, sorry, it was a submodule of F0, hence has no non-trivial 0 divisors. So this is free, So X, non-zero divisor on K1. And continuing in this way at every step, we get exactness all the way out. So continuing, we get exactness at every term. And so it remains a resolution. Okay. Very good. So that's this third change of rings theorem. And we have a corollary. Corollary is the following. So same hypotheses. A Noetherian local M finitely generated, X non-zero divisor on A and M. So it should be, I don't want it to be a unit, it should actually live in M. And so in the previous theorem, I allowed the case that the resolution was infinite. And then modulo x, it'll still be infinite. So that would be the case of infinite projective dimension. If I specialize to the case of finite projective dimension for my module, then I got that the projective dimension, well, I could reduce M modulo x, and that would give me an A mod x module, but then I could restrict it again to be an A module. That was something we did in the first change of rings theorem, I think it was called. So the claim then is that this will be 1 plus projective dimension of A over M. So if I reduce mod x and then restrict, I increase the projective dimension by 1. And the proof is easy now, given what we said before. So we have the left-hand side, projective dimension of M mod xm. So by what was called the first change of rings, this is 1 plus projective dimension over A mod x of N mod x. And then by this third change of rings theorem, this last term is this. Okay, so we're going to use this corollary next time, I think, to control inductive arguments where I have some local ring and I'm going to take a modulo some variable x and then another variable x and so on, and I'll produce things of bigger and bigger projective dimension. And I want some bounds under that, under some hypotheses. I think they're doing Weierstrass P function, which is much cooler than what we're doing. Okay, so that's it for the change of rings theorems. And now to get any further in the homological theory of local rings, we need to know a little commutative algebra. And maybe you don't know much commutative algebra, so I have to tell you some things. If I don't remember to readjust, please shout at me. So this will be a review. Maybe you know something. So review of dimension theory. Of Noetherian rings. Noetherian commutative rings. So this is all stuff you do in a standard commutative algebra class. We're not doing anything fancy. And most of it is pretty easy to prove. There's one important theorem which is a bit tricky. So definition. So the curl dimension of a commutative ring A is the supremum of lengths of chains of prime ideals so how should I do it? So the length, the thing at the top doesn't count. That's going to be in degree 0. So this is a chain of length 1. P2, and so on like this. Maybe it's infinite. You take the supremum over all such things. If there's an infinite one, it's automatically going to be infinite because I can take, in the supremum, I can take the next longest one, the next longest one. But it can happen sometimes that every given chain is a finite length, but there's no universal bound on the length, and so it's still infinite in the supremum. Okay, so that's the definition. And simplest examples. So in general, it takes more work to produce more complicated examples. But simple examples are principal ideal domains, such as the integers or a polynomial ring over a field. So these are principal ideal domains. Every ideal is shared by a single element. It's prime exactly when that element is irreducible. Okay, so every chain, so maximal chains look like 0. The domain, so 0 is a prime ideal, and some principal ideal generated by an irreducible element. And so in these cases, the dimension is 1 in a principal ideal domain. And we'll eventually see more complicated examples. You can also prove, it's not that hard, but uses purely algebraic techniques instead of homological techniques, that the dimension, the Krull dimension of a polynomial ring of many variables is the number of variables. So this is if K is a field. Otherwise, if K were some other commutative ring of some finite dimension, you would take that dimension plus these. If it were a domain, I think you might need it to be a domain of some dimension plus the number of variables. Okay, so definition. Given a prime in a commutative ring, so I'm always going to write A for commutative rings to distinguish them from R, a general ring. So given a prime ideal, the codimension codimension P is the supremum of lengths of primes descending from P. Of chains of primes descending from P. And note that the codimension of P is 0 if and only if P is minimal. There's no other prime contained in it. So in a domain, the minimal primes are 0. That's it. But in a general commutative ring, you might have a number of minimal prime ideals. So this codimension is geometric language. It has to do with, if you think of the ring as functions on its so-called spectrum, then every ideal defines some kind of subspace of that. This is the codimension of the subspace defined by this prime ideal. Sometimes, especially in more algebraic books, it's called height instead of codimension, which I guess is also kind of a reasonable name from this point of view. It's how high up it is. But from the geometric point of view, it's not. You know, the order gets switched, and so it's codimension. But there's one real theorem that we need about the codimension, and then that's the only non-trivial thing we need from commutative algebra. Okay, so let me give you some facts about dimension and codimension, maybe mostly about codimension. So in a Noetherian ring, first one, oh, I'm supposed to change screens again. So in a Noetherian ring, every prime has finite codimension, even if the ring is infinite dimensional. So all the descending chains have finite length, but in general, maybe there's no universal bound on that length. 2, Accruals dimension theorem. Maybe it should be called codimension theorem, but for some reason it's called dimension theorem. So it says if I, so this should probably be Noetherian as well. So everything A is going to be a Noetherian ring. Everything is taking place inside some fixed Noetherian ring. So if I is some ideal, so Noetherian means all ideals are finitely generated. So suppose I have an ideal generated by R elements. Then the codimension, then for any prime P minimally containing I, so there's no other prime in between I and P. the codimension of P is at most R. So there's a particular case of this that's called the principal ideal theorem. The principal ideal theorem is the case where I is a principal ideal. So it says if P, a minimal prime containing some element, then the codimension of P is at most. So this is like saying, if I have a function on some space, I expect it to vanish along a hypersurface, but not of something smaller than a hypersurface, not something of codimension 2. Okay. Third fact we need is called Curl's intersection theorem. So now I need A to be Noetherian local, not just Noetherian. So in this case, I can look at powers of the maximal ideal, and I could intersect them. And the claim is that that's 0. So if I had an element which is an m and an m squared and an m cubed and so on, then it must actually be 0. And this should be kind of intuitive, at least in examples. So a maximal ideal, for instance, in a polynomial ring and many variables, it might look like it's just generated by the variables. In nice cases, every maximal ideal will look like that up to a change of coordinates. And then being in a higher and higher power means that your polynomial is, well, it's at least quadratic, it's at least cubic, it's at least quartic, and so on. So in the end, it must be 0. Four, there are finitely many minimal primes in a Noetherian ring. Probably we'll need this fact at some point. It's not hard, using the definition of Noetherian. Five, we have what's called prime avoidance. One form of which says the following. So if I have one ideal contained in the union of a bunch of other ideals, say finitely many of them, and suppose at least 2 of them are prime, then the only way this can happen is if J is actually contained in one of the ideals from the right-hand side. Okay, so these are the facts we need from commutative algebra. Most of them are pretty easy to prove. Maybe we'll spend some time on some of them in the seminar. The only one that really takes some cleverness, once you see the proof written down, it's not hard, but maybe you wouldn't come up with the proof yourself, is this principal ideal theorem, which you use in proving the generalization. This is not so hard, but there's something to do, and the rest of them are pretty easy. So these are the facts we're going to take as given. maybe this one I could even deduce from other things. So let me give this as a proposition. So now we'll prove a few things that follow from these facts to kind of warm up. Yeah. So we'll prove this as a consequence of other things. So proposition, in a Noetherian ring, all primes are a finite codimension. So in a Noetherian local ring, so a Noetherian local ring is finite dimensional. That's not true for a general Noetherian ring, but it's true for the local ones, because local means there's a unique maximal ideal. Any other prime is contained in the maximal ideal. So any descending chain at the top, if it's maximal, must start with the maximal ideal, and that's a finite codimension. So the proof is just Accruals dimension theorem. So in a Noetherian ring, every ideal is finitely generated. So by Accrual, it has finite codimension. Very good. And now we want to focus on the case of Noetherian local rings. So proof, proposition. Does this appear in the screen? It looks like I forgot to move the board again. Okay. So proposition, if A is Noetherian local, then I have the curl dimension of A, supremum, length of a maximal chain of primes. We know that's finite. And for an Noetherian local ring, it's bounded by something that's easier to compute. Namely, I have the residue field, A mod M, call it K. And over that, I have a preferred module, which is M mod M squared. This is called the Zariski cotangent space for some reason. It's related to derivations and differentials. So proof. Let n be this dimension. Then you'll remember what we proved about Nakayama's lemma. We said that if I had a finitely generated module over an Noetherian local ring, and I wanted to know what a minimal set of generators looked like for it. A set of generators was a minimal set of generators if and only if modulo the maximal ideal that gave a basis. So in order to find a minimal set of generators for M, I can choose a basis for M mod M squared. M mod M squared is M tensor A mod M. So choose minimal generators for M, call them f1 through fn that reduce to a basis. Okay. And now we're going to look at A mod f1, A mod f2, and so on. Okay. So then, let's look at dimension of A. And let's compare that to dimension of A mod f1. So dimension of A mod f1, I could by the principal ideal theorem, I could lose a minimal prime containing f1 has codimension at most 1. So my dimension has dropped by at most 1. So I can get an inequality like this. So this is by Accruals principal ideal theorem. And then proceeding, I have dimension of A f1 is less than or equal to, by Accruals theorem, I could quotient by f2, and I will get this. So in the end, I'll get dimension of A is less than or equal to dimension of A modulo everything plus n. But now modulo everything, that's the residue field. And the dimension of a field is 0 because there's a unique prime ideal, namely 0. So there's no chain of positive length. So this is just n. Okay, so this follows from the principal ideal theorem. So we get this bound on the curled dimension, which is, curled dimension can be hard to understand because it's you're looking in the local ring case for the maximal length of a chain of prime ideals. But maybe you have no idea what all the prime ideals are in the ring. That's, in general, can be very hard to know. On the other hand, the right-hand side can be pretty easy to compute. It's a kind of linear algebra problem. So we get a bound. And I need to move this again. And anytime you see a bound, it's natural to ask, when is it achieved? Something special must happen when this is an equality. And that's the definition of regular local ring. So definition, a Noetherian local ring is called regular if this is bound is achieved. So the curl dimension equals exactly the dimension of M mod M squared as a vector space. So let me give two simple examples, and then eventually we're going to have a characterization that allows us to give more examples. So I could look at the integers. That's not a local ring. There are many maximal ideals, one for every prime. But I can localize it at a prime. So this means inverting all the stuff that's not in the prime. So this is a ring of fractions like this, where b is not divisible by p. So you can take that as a subring of the rational numbers if you like. Okay. Then in this case, the stuff where the numerator is divisible by p forms a maximal ideal. And then the only other prime ideal is 0. So this has maximal ideal generated by p, and 0 is the only other ideal, only other prime ideal. So it has dimension 1. On the other hand, this is the maximal ideal. On the other hand, the residue field we're taking this modulo p, and you can check that that's just fp. That's the same as if we had taken the integers modulo p. So that's our residue field. And m mod m squared will just consist of 1, 0, let's see, how do I want to say it? So this will be one-dimensional. It will be one-dimensional, generated by, I guess I could write them out. Okay, so let's write down a basis. We will write down a basis in the seminar. This will be a nice exercise, and we'll also do it for same, but instead of the integers, we'll take a polynomial ring over a field, and we'll invert everything outside of the maximal ideal generated by t. Okay. So now, so these are regular local rings because the curl dimension was 1, and this is also 1. Okay. So M is principal, and so I know that's a minimal generating set, therefore it forms a basis modulo M squared. Okay, so lemma. I want to be able to do inductive things with regular local rings. So say A is a regular local ring. This always implies Noetherian under my definition. So maybe I should say, well, I'm going to let it be implicit. So regular local ring implies Noetherian. And suppose M has a minimal set of generators, F1 up to Fd. So now I'm writing D instead of N because the dimension of this space M mod M squared and the dimension of the ring are the same. So this is minimally generated. Then I could take the quotient by the first, say, I elements. And the claim is that this is a regular local ring. Is again a regular local ring. of dimension d minus I. So each time I impose an equation, the dimension drops by 1. Okay. So in a general ring, that doesn't always happen. It's one feature of regular local rings that it does. It behaves like your geometric intuition when you impose equations in some nice affine space. It's also saying the equations are kind of independent, so that at each step, when you impose an equation, the dimension drops by 1. So is again a regular local ring of dimension d minus I. Okay. So I want to make some observations. So by induction, it's enough to figure out what happens after imposing one equation. It's enough to understand A mod F. And so let's call this A prime. And I want to compare the maximal ideal of A to the maximal ideal of A prime. So note, we have the following. I have a short exact sequence. Okay. We will eventually know this is short exact, but for now we just know that it's right exact. It will turn out that regular local rings are domains. We will prove this. But for the moment, we just know that it's right exact. Multiplication by f, and then the quotient is A prime. And I also have reduction modulo m. That's the kernel here. And similarly here. So this has some maximal ideal m prime. Okay, so the bottom row is short exact. The top row is right exact. And so I can apply the snake lemma here. So the co-kernel here is 0. And so in the kernel here is A. Okay. So the snake lemma so by the snake lemma, we see that m prime is surjected onto by m because the next term is 0 in this long exact sequence. And what is the image here? It's multiplication by f. So we see that m prime is m modulo f. And next, we need to understand m mod m squared versus m prime mod m prime squared. So we'll do another snake lemma argument. So let's consider m squared, m mod m squared. We know m surjects onto m prime. Yes? And inside of that is m prime squared. And what is this? It's a sum of pairs of products in M prime. And each thing that appears in a pair of products comes from M, so this is also surjective. So I have two short exact sequences like this. these two are surjective. Therefore, this one is surjective also. And I know that the kernel of this is generated by f. So whatever the kernel is here is generated by the image of f, modulo m squared, which is just the reduction of f. So the kernel of this map is generated by a single thing, a single vector in this vector space. So the dimension over k of m prime mod m prime squared equals dimension of m mod m squared minus 1. I know that this vector is non-zero because it was part of a generating set of the maximal ideal, so reduced modulo m to a basis. Okay. Okay, so the dimension dropped by exactly 1. And now, by Accruals' principal ideal theorem, the dimension of A mod F, it's at least as big as the dimension of A minus 1. So Accruals' principal ideal theorem is about codimension, but in the Therian local case, we don't have to worry about the supremum not being achieved. I mean, you know, every chain of maximal ideals at the top has our maximal ideal in it. That's fixed. And so I can actually rewrite it in terms of dimension like this. On the other hand, by the general observation about local rings, I know that this dimension is bounded by the dimension of m prime mod m prime squared. And we just saw that that was equal to dimension of m mod m squared minus 1. And by hypothesis, A was regular, so this is just dimension of A. Okay, and so the dimension of this is exactly dimension of A minus 1. That was the claim. And so this allows us to do inductive arguments on regular local rings. So what do we have, about 14 minutes? Okay. I think we have time for one more thing. So I want to prove that a regular local ring is a domain. This is not obvious, but it's an important fact. Okay. Maybe I'll call this a theorem. So a regular local ring is a domain. So we're going to induct on the dimension of A. So if the dimension is 0, then, well, it's a local ring, so there's a unique maximal ideal. But if the dimension is 0, there are no other primes. So if dimension is 0, then M equals 0. Okay, therefore it's a field. Remember, in a local ring, we saw in the seminar that the units are precisely those things outside the maximal ideal. So since everything outside the maximal ideal is a unit, of a local ring, is a unit. That was a feature of local rings. The units were precisely those things outside the maximal ideal. And so if everything that's not 0 is a unit, then of course it's a field. Okay, so now suppose it's true for dimension equals to d minus 1. And we're going to use this kind of inductive argument. So choose probably, yes, I'm on the correct screen. So choose F in the maximal ideal, but not in the maximal ideal squared. We can do that because we know that the quotient is positive. So M does not equal M squared. We know that the quotient is positive dimensional. So choose F in M, but not in M squared. Then by induction, then A mod F is regular local dimension d minus 1 by what we just proved. So by the previous, was it a lemma that I called it? My previous lemma? Lemma, yes. By previous lemma. Very good. So actually, I have here the proof that Weibull gives, which uses this Corollary intersection theorem and prime avoidance. However, it might actually be easier than this. Just a minute. Maybe not. No, okay. Right, so by induction, A mod F is a domain. We want to see A itself as a domain. So when I pass to A mod F, maybe I lost some primes that were in A. Yeah? For instance, those that are contained in F. But all the other ones, if they contain F, they become primes in the quotient. In particular, the ideal generated by F has to be prime if the quotient is a domain. So what we want to see that A is a domain is that 0 is a prime ideal. Okay, so let's look at primes that are contained in F. So consider a prime contained in F, a prime properly contained. I use a rational notation in which this means properly contained, just like if it were a strict inequality. So then and there must be one, right? Because the dimension dropped. So the chains of prime ideals became shorter. So I must have lost something in one of the chains. So this must exist because chain length has decreased in the quotient. Now, if P is contained in F and P is prime, then P is contained in any power of F. Because, let's see. How to say this? I want to use the fact that P is prime. So things that are in power of F look like some little a times F to the power n. Just a minute. So let's try to check this. Let's suppose, so P is in F. So for all, let's say A in P, A equals some A prime times F, because it's contained in this ideal, right? However, P is prime. So that must mean either F is in P or A prime is in P by primeness. However, F can't be in P, otherwise this containment would not be proper. So that implies A prime is in P. So A prime equals A double prime F. And then inductively, well, then that means A equals A double prime F squared. And then A double prime will again be in P, and so on. Okay, so inductively, P will be in any power of F. And now we'll use Curl's intersection theorem. So by Curl's intersection theorem, I have that now P is contained in the intersection of all powers of F, but F was contained in M, so that's contained in the intersection of all powers of M, which is 0, by the intersection theorem. So P equals 0. So A is a domain. And maybe I could have justified this step a little more, that P, there must exist a P which is strictly contained in F. Let me maybe give a little more explanation for that. So claim. If no P properly contained in F, then A is not a domain. Actually, do I need that? Yes, then A is not a domain. So that's not a claim. That's just a fact. Because then, for instance, 0 would not be prime. But then F would be minimal prime for all F of the form which is an M but not an M squared. But then, if that's the case, the maximal ideal M would consist of stuff that was an M squared plus all of the minimal primes. I know there are finitely many of those. Because everything else that's not an M squared would generate a minimal prime. So by prime avoidance, the maximal ideal would be a minimal prime. For some I. And we would have dimension 0. So that would be a complete argument in case you were worried that maybe this f was chosen in such a way that it didn't intersect one of the chains of maximal length. Okay, so let us stop there. We have seminar as usual.